Our team of Penn State undergraduate engineers is tasked with identifying a design component for a composite impeller to replace Wabtec's time-tested and field-proven aluminum impeller. Our goals are to research and identify a composite material that reduces cost while also meeting Wabtec's list of critical performance requirements. The impeller must be able to survive spinning at 3,900 RPM at 300 degrees Fahrenheit and exposed to environmental conditions from the desert to the tundra for a life of 20 plus years.
In this table are our top 3 choices of composites to be used in the construction of Wabtec's impeller fan. Our first choice is carbon fiber with bisphenol A epoxy, which exhibited the least amount of radial stress deformation during our FEA analysis. Our second option is bezalamide resin with carbon fiber. It has excellent material properties but a high barrier to entry, as bezalamide is mainly used in aerospace. Finally is S-fiberglass with bisphenol A epoxy. Its properties are not as good as the first 2 options, but it meets the specifications set forth by Wabtec.
Our team decided to add metal tubes into the composite material to relieve compressive loads from the bolts, preventing crack propagation. We have designed the tubes with a flare on the top and the bottom to prevent them from backing out of the material. In addition, the tube surfaces are designed to have a slate offset from the composite surface so that there is no direct contact between the bolt and the composite when the tubes are under compressive load. We have chosen A356 aluminum because it matches the coefficient of thermal expansion and the elastic modulus well. It also will maintain the strength needed to support the bolt compressive loads.
Our team used ANSYS simulation to model our impeller. Our team noticed the highest stresses in the outer radius of the impeller, as noted by the light blue color in the top left figure. The fan was modeled as an anisotropic material with the strong axis in the direction of the red arrows as indicated in the bottom left figure.
Now we will move on to balancing suggestions. The balancing specification that Wabtec has outlined in their current assembly level drawing is to design a composite impeller that, when in operation, will maintain dynamic balance and will not exceed an imbalance of 1 ounce-inch. To satisfy this balancing requirement, we are going to replace the rivets from the current metallic impeller design with epoxy filament counterbalances. This is because rivets create stress concentrations that can damage the fibers and weaken the structure, unlike metals that tolerate point loads better. Composites perform best when loads are distributed over larger areas, preventing delamination and cracking from stress concentrations. We plan to design the epoxy filament counterbalances in crescent-like shapes. A crescent shape handles stress better than other shapes because this shape has a more gradual geometry change. Additionally, the shape allows for more precise radial placement, more symmetrical freedom, and easier mass adjustment through a controllable thickness, angle, and radius. This will allow us to fine-tune the exact ounce-inch specification provided by Wabtec.
The manufacturing process we selected to recommend was vacuum-assisted resin transfer molding. We chose it because it forces the resin to flow to all parts of the complicated geometry. This limits the likelihood of voids and delamination issues later in its use. After an initial setup cost for molding and machine costs, this process allows for the desired price point across all units.